So in this lesson, we're going to compute volume of revolution using the washer method. So the washer method is similar to the disk method, except now we'll have a hole inside our disk. So if you consider two functions, f of x and g of x, consider them both being positive between a and b and continuous, and consider a planar region bounding f and g from a to b. And so now take that region and rotate it about the x-axis to construct a solid object. Now that solid object is going to have a hole through the middle. And so to compute volume, we have to account for that hole in the middle. And so we have to, if we take a cross-section of this volume of revolution, or of the solid of revolution that's created, you see what's to the right. We have this annular region, or this annulus. So the annulus has an inner radius, I'll call it r sub I, and an outer radius, r sub O. And the area of this annulus, or I'm calling it the area of the washer, is basically a difference in areas. So it's going to be a pi r sub O squared minus a pi r sub I squared. And of course you can factor out pi. This is the area of the washer, and this is going to be used as a basis for computing the area of the actual washer, which will have some width. And if you look at the figure, the width of the washer is delta x. So basically, if we wanted to compute volume of a washer, it is the area of the face of the washer, which you see here, pi times this r sub O squared minus r sub I squared, times delta x. And so if we construct an approximation for this volume using a sum and then take a limit as n goes to infinity, we get the following equation for the volume of this solid object. So the volume is going to equal, using the washer method, it's going to be pi times an integral from a to b, and it's going to involve taking f of x and squaring it. That's going to be our outer radius, and then subtracting g of x squared. And so I'm going to leave out the details of constructing this sum and then taking a limit. You can look at the book for more of the details. You can also look at the book for figures of these solid objects, which are a little tricky to plot. So this is the formula for the volume, and let's try an example. So in this first example, we're going to consider f of x equal to x squared plus 2 and g of x equal to 4 minus x squared. And we're going to find the region, or find the volume of the solid object that's formed by taking a planar region bounded by these two curves and rotating about the x-axis. So for a picture, so a plot of 4 minus x squared, all right, so it has a y-intercept of 4, has roots of plus and minus 2. This is what a plot of g of x looks like. And for a plot of x squared plus 2, x squared plus 2 looks something like this. So we're taking this region here and rotating about the x-axis. So this is x squared plus 2, and this is 4 minus x squared. And I'm going to make some changes here. I don't want to confuse you by calling one function f of x and calling the other function g of x, and making you assume that the f is going to be bigger than the g in this case, we'll think about which function is bigger than the other, or what's going to be the outer radius and what's going to be the inner radius. All right, so we're going to be rotating about the x-axis, and if I construct a representative rectangle, so here's a representative rectangle, has width delta x, okay? The inner radius of this rectangle that we're rotating about the x-axis, that's going to be can turn into a washer. The inner radius is this distance here. This is the r sub I. The outer radius, I'll try to go out this way. The outer radius is this distance here. This is r sub O. Okay? So for this problem, think about what r sub O is. So the outer radius, if you look, is the curve 4 minus x squared. So r sub 0 is equal to 4 minus x squared. And the inner radius, well, the inner radius is the other function. It's x squared plus 2. So, and now we can go to our formula, and yeah, I have the formula written as an f of x minus g of x. In this case, the f of x is really the 4 minus x squared, and g of x is really the x squared plus 2. So if we plug these things in, right, and I guess if we compute f of x squared in this case, so f of x squared, so I'm going to compute some things outside of the integral. So f of x squared equals, in this case, our 4 minus x squared is f of x. So if we square this, we get, using FOIL, we get 16. And then there is a minus 8x squared, and then plus x to the fourth. And then g of x squared is x squared plus 2 quantity squared, which equals x to the fourth plus 4x squared plus 4. So now our integral becomes, we want, in this case, f of x quantity squared minus g of x quantity squared inside the integral. So our volume is pi integral from limits of integration. Have we determined those? We have not actually determined the limits of integration, and those are going to come from points of intersection. So, so let's actually erase this, and let's find points of intersection. So the points of intersection come from setting 4 minus x squared equal to x squared plus 2. So if we rearrange things, this turns into the equation 2x squared minus 2 equals 0. And so if we solve this equation, we get x equals plus and minus 1. So those will be the limits of integration. And so now if we put all these pieces together into our formula, remember, here is our formula for volume. So our volume is equal to pi times an integral from from minus 1 to 1. F of x squared minus g of x squared. Let's go back and see what that's going to be. So here we have f of x squared and g of x. If we subtract the two, we can actually subtract the two as we see them here. So we will get the x to the fourths will cancel. We end up getting a minus 8x squared, then minus a 4x squared. That's going to be minus 12x squared. And then the 16 minus 4 will be positive 12. So inside the integrand, or the integrand will be minus 12x squared plus 12 dx. This will be the volume of that solid object. So finding an antiderivative is quite easy. I'm just going to write down, you could check this answer. I get that the volume is equal to 16 times pi. One of the things that we could have used in this problem was symmetry. If you notice that the planar region that we rotated about the x-axis had some symmetry, we could have actually considered just half of this solid object. Okay, that is, consider the planar region from 0 to 1, and then multiply the volume by 2. In any case, the volume turns out to be 16 pi. So now consider taking the same planar region, and instead of rotating about the x-axis, let's rotate about a different horizontal line. Okay, remember the x-axis is a horizontal line. It is the line of the equation y equals 0. So what if we wanted to rotate about some other horizontal line, y equals, let's say 3, or let's say minus 3. So I'll say now, let's rotate about y equals minus 3. So I'll draw a picture again. So we had our 4 minus x squared we have our x squared plus 2. We have our line. This is called our axis of rotation. This is our line, y equals minus 3. So now what we're going to do is we're going to rotate about the line y equals minus 3. So if we construct a representative rectangle, has width delta x. Okay. Busy? Okay, so to determine the inner radius and outer radius in this case, let's see, if we look at what the inner radius is, this is the inner radius. You can think about what that is, and the outer radius is this distance here. So now, what's changed? Think about what the outer radius was previously, what the inner radius was previously. What do you think the outer radius is now? Well, it still involves the curve of 4 minus x squared. But what do we have to do now with this 4 minus x squared? You can think about this. Don't be confused by the fact that we're rotating about the line y equals minus 3. So if you compare r sub o in this case to r sub o in the previous case, what's happened? Well, r sub o is bigger now, right? And how much bigger? It's bigger by exactly 3. So r sub 0 in this case is 3 plus 4 minus x squared, or it's equal to 7 minus x squared. And what is r sub I? Well, it's related to the curve x squared plus 2. Of course, we have to add 3 now to that as well. So we do 3 plus x squared plus 2, and we get x squared plus 5. Okay, so this is our these are the outer radius and the inner radius respectively. So the volume that we need to, so the formula for the volume, or this integral that we need to set up, looks like the following. So our volume is now pi times an integral. We still integrate from -1 to 1. We could use symmetry, but we're actually just going to set up the integral, and then I'm just going to write down, give you the answer. You can check on your own, but it's the outer radius, which is 7 minus x squared, and we square that, okay, and then minus the inner radius, which is x squared plus 5, and that gets squared, and then I can close off the brackets. In this case, we're not going to FOIL things. We'll just set up the integral and assume that everything else from here is a routine computation. If you want to check your answer, this volume turns out to be 32 pi. And hopefully it makes sense that this value is larger since we're rotating about an axis that's further away. So it's 32 pi is the answer.